Hello calculus students and general seekers of truth. Welcome to the video lesson on differential equations and in particular logistic equations. So here I have an example and we're going to start from the basic concepts and then really tackle the example. Okay. So it says here, population of bacteria grows logistically. Suppose the initial population is 3 milligrams and the carrying capacity is 100 milligrams and the growth parameter is 0.2. Find the differential equation satisfied by the population. Find a function that represents the population at all times, and when will the population reach 900 milligrams or 90 milligrams? When will the population's rate of change start to decrease, and when will the population reach 200 milligrams? Okay, so what I'm going to do is go back to the basic idea that a differential equation looks like this for logistics. dp dt, the rate of change, is proportional to the population and then times 1 minus the population over k. All right? So we talked about this before. R here is the growth parameter, and K is the carrying capacity, and I'll explain a lot about that and why that's called the carrying capacity. And so we can answer part A right now, and we can say that this is the differential equation, so it would look something like this. dp dt is equal to the growth parameter, which is 0.2 p1 minus p over the carrying capacity, which is 100. Okay, so that's part A. Part B, find a function that represents the population at all times. That basically means to find P of t. And what I'm going to do here is I'm going to find P of t using the generic version first, and then I'll plug everything in at the end. It's just so that you get the sense of how to solve these differential equations. And it's really, you're really solving the same equation over and over again. So I'm just going to solve it one time using all of the abstract constants here. Okay, so here we go. We're going to start by separating the variables. So I'm going to get all of my everything that has the variable p in it on one side. So dp over p times 1 minus p over k is equal to r dt. Then we are going to integrate both sides. Now on the right side, that integral is very simple. It is simply rt plus a constant, because r is a constant and we're integrating with respect to t. So we have rt plus a constant. Over here, we are going to use partial fraction decomposition. Okay. So if you're not familiar with that, look back at the videos on that lesson. But basically you have 1 over p times 1 minus p over k is equal to some constant a over p plus some constant b over 1 minus p over k. So we're taking a single fraction and we're representing it as the sum of two other fractions. And when we take this sum here and add them and find the LCD, the least common denominator, we'll get the same thing as this, but we'll be able to do some nifty things in order to solve for the constants a and b. So we multiply a by 1 minus p over k plus b over p, plus b times p. Our common denominator is going to be p times 1 minus p over k, and the same thing over here. Right? And since the denominators are the same, we can cancel them out. And if you look at this equation is true for all values of p, so we can select any convenient values that we like. And a good convenient value in this case would be 0. So if p equals 0, then you have 1 equals, a times 1 minus 0 over k plus b times 0. That's gone. That's gone. And you end up with 1 equals a. Then we can let p equal to some other value, and we want it to be something very convenient, so let p equals k. And so now you have 1 equals a times 1 minus k over k plus b times k. Right, so this evaluates to 1. 1 minus 1 is 0, so that's gone. So we get that 1 over k is equal to b. Okay. So our original integral over here can now be separated as follows. Instead of this expression, we can separate it into the integral of a over p. So a in this case is 1 plus p, plus b over 1 minus p over k. So, but b is just 1 over k times 1 over 1 minus p over k. All right. I can actually do a little bit, and this is all with respect to p. And oh, don't forget, this whole thing here is equal to RT plus a constant, which was the right side of our equation from above. Okay, so I can take this a little bit further, and I get the integral of 1 over p plus, and when I multiply all this out, I get 1 over k, and then minus, and I'm really just distributing this k throughout, so k times 1 is k, k times p over k is p. dp is equal to RT plus a constant. Okay. So far, very little calculus, just lots of algebra here, and now we're finally ready to do some integration. Alright, so when I integrate, I get the natural log of the absolute value of p plus the natural log of k minus p, absolute value, times, now keep in mind here, when we integrate, this is not p, this is negative p, so we have to take the chain rule into account. So that's negative 1 equals r times t plus a constant, and this is the natural log of p minus the natural log of k minus p equals rt plus c. And then I can use the quotient rule of logarithms, so that'll give me the natural log of p over k minus p equals rt plus the constant. And by doing this, this step from the second to last step to this point is really necessary for me in order to solve this in terms of p. So I rewrite this in exponential form, and that gives me p over k minus p is equal to e to the rt plus c. But of course, e to the rt plus c is the same thing as e to the rt times e to the c. Okay, and e to the c here, e is a constant raised to some constant, so that's still a constant. Okay. And now I'm going to solve for p. Okay, so I'm going to solve this by dividing both sides by ce to the rt and multiplying both sides by k minus p. Then I'm going to add p to each side. Okay. This is all equal to k. And then in order to get the common denominator, I'm going to multiply this by CE to the RT over CE to the RT. So putting all this together, we get P plus P CE to the RT over CE to the RT equals K. Then multiply both sides. Multiply both sides by the denominator here, and we get KCE to the RT. We're almost there. It's a long problem, but it's just lots of algebra. Factor out a P, so we get 1 plus CE to the RT on the left side equals KCE to the RT. Then finally, P is equal to KCE to the RT over 1 minus CE to the RT. Okay. Now, I'm actually going to go, this is technically done and correct, so I'll call this star because we're actually done here. But I'm going to go a couple steps further, and I will explain why I do that towards the end of this series of videos here. But I'm going to go a few steps further here. Okay. So I have P equals KCE to the RT over, and this should be a plus. I don't know, it was a plus up here. I don't know why I wrote minus, but in the denominator, what I'm going to do is I'm going to factor out CE to the RT. Going to factor it out of both terms here. Now, the last term, I'm just going to get 1, so that's simple enough. And the first term here, I'm factoring CE to the RT out of 1, so I'm really just taking the reciprocal of this. So this is 1 over C e to the negative RT. And so again, all I'm doing is I'm factoring this CE to the RT term out of the denominator. And I do that so that I can cancel it in the numerator. Okay. And my final answer is K over 1 plus 1 over C. Now keep in mind that C is a constant. So 1 divided, the reciprocal of a constant is still a constant. So C e to the negative RT. Okay. Whew. And we got to the end. Okay. So this is a nice solution, a nice clean solution. And again, I will explain this a little bit later as to why I did this, as to why I didn't stop here. This form is more commonly used, and not only that, it's more convenient for us. So now I'm going to go back and solve the actual problem. Okay. So we know a few things. The initial amount is 3, and the growth parameter is 0.2. So and the carrying capacity is 100. So I can fill this in for part B. P of T is equal to, carrying capacity is 100, that's K, 1 plus CE to the negative RT. Now R was 0.2, that was given to us in the problem. And then we know that P of 0 is equal to 3, that's the initial condition. So 3 here is equal to 100 over 1 plus CE to the negative 0.20. Now e to the 0 is just 1, so we can get rid of that. So cross multiply, and we get that 1 plus C is equal to 100 over 3. Therefore, C is equal to 100 over 3 minus 1. Okay. So let's see, that's 97 thirds. Okay. So my final answer is P of T is equal to 100 over 1 plus 97 thirds e to the negative 0.2 t. And that's the solution to part B. Okay. Alrighty, so this is getting to be a lengthy video, so I'm going to end it here, and I will continue another one that will solve the remaining parts of the problem.